Today, we're digging deep, and I mean literally, into these powerful invisible forces that are constantly squeezing, stretching, and yeah, Okay, so picture this. You've just spent millions of dollars drilling a well, thousands of feet straight down into the Earth's crust. Everything seems fine, totally stable. And then, bam, without any warning, the rock around it just fails. The whole thing collapses. What kind of unseen force could possibly cause something that catastrophic? Or, hey, what about earthquakes? We all know they happen along faults, right? But what decides if the ground is going to pull apart, or get smashed together, or just slide sideways past itself? It's a huge question, and believe it or not, the answer to both that and the collapsing well is the exact same force. It all comes down to this ever-present, invisible pressure that we call tectonic stress. And trust me, getting a grip on this is absolutely critical for, well, for everything from finding energy to predicting some of the most dangerous geological hazards out there. All right, so let's jump right in. What exactly is this invisible pressure? At its heart, the idea is pretty simple. Stress is just a force that's acting over a certain area. But when you go deep underground, that force isn't just coming from one direction. Oh no, the rock is being squeezed from above, from below, from all sides at the same time. It's this incredibly complex, three-dimensional pressure cooker down there. So to make any sense of this, scientists had to simplify things. And they had a brilliant insight. They realized that because the Earth's surface is just, air or water, it can't really support any side-to-side forces, what they call shear forces. And that little fact means that one of the main pressure directions is almost always pointing straight up and down. That one idea is a total game changer, because it lets us describe this whole complicated mess with just three simple values. And these are what we call the three principal stresses. First, you've got SV. That's the vertical stress. That's the easy one to wrap your head around. It's just the crushing weight of all the rock piled on top of you. Simple. Then you've got two horizontal stresses. SH max, which is the maximum horizontal squeeze, and SH min, the minimum horizontal squeeze. And that's it. With just those three numbers, we can actually start to understand and even predict how the Earth's crust is going to behave. Okay, so now let's see how these three values come together to create this really powerful system for classifying whole tectonic regions. This is where it gets cool. So here's the key takeaway. It's not just about how much stress there is. The really important thing is how those three principal stresses stack up against each other. Which one is the strongest? Which one's the weakest? Just by ranking them, we can figure out exactly what's happening to the crust, whether it's being stretched out, sheared apart, or squeezed together. Let's start with the first one, the normal faulting regime. In this situation, the vertical stress, that SV, is the big boss. It's the strongest force of the three. Basically, gravity is winning the tug of war. Since the horizontal pushes are weaker than the downward pull of gravity, the crust is literally being stretched apart or extended. The best way to picture it is like stretching a piece of taffy. You pull it from both ends, it gets thin in the middle, and eventually it breaks. That's exactly what's happening in places like the East African Rift Valley. All right, next up is the strike-slip regime. Now, in this case, the vertical stress, SV, is kind of stuck in the middle. It's the intermediate force. The strongest push is horizontal, and so is the weakest one. So what does that mean? It creates a situation where the easiest thing for the rock to do is just slide sideways. You get these massive blocks of the Earth's crust grinding horizontally past each other. A great way to think about it is to put two big books next to each other on a table and just slide them in opposite directions. That's the exact motion you see along the famous San Andreas Fault out in California. And that brings us to our third and final one, the reverse faulting regime. And this one's a bit of a mind-bender. Here, the vertical stress from gravity is actually the weakest of the three forces. The sideways squeezes are both more powerful than the weight of the rock itself. This means the crust is under intense compression. It's being squeezed from the sides like it's in a giant vise. And all that pressure has to go somewhere, right? So it forces huge blocks of crust up and over each other, building up massive mountain ranges. This is literally how the Himalayas were built. Okay, so this raises a pretty obvious question. If this force is invisible, it's incredibly powerful, and it's happening miles underground, how in the world do we actually measure it? Well, the answer is pretty amazing, and it comes from the act of drilling itself. See, when you drill a deep hole, you completely change the stress right around that opening. The rock has to deal with this new situation, and the way it fails, the way it breaks under all that pressure, leaves behind a perfect trail of clues for us to follow. And there are two main clues we look for. First, on the sides of the wellbore where that horizontal squeeze is the tightest, the rock actually gets crushed. It fails in compression, and we call these breakouts. And here's the cool part. They always line up with the direction of the minimum horizontal stress. Then on the other sides, where the squeeze is the weakest, the rock can actually get pulled apart, creating these tiny little cracks or drilling-induced fractures. And you guessed it, they point in the direction of the maximum horizontal stress. So you put them together, and these two things act like a compass, pointing out the exact orientation of the stress field miles beneath the surface. Now, look, a single measurement like that is super useful. But what happens when you start to collect thousands of these measurements, from wells, from earthquakes, from all over the entire planet? Well, that's exactly what a huge international team of scientists did. In this massive project called the World Stress Map, researchers from over 30 countries pulled together almost 10,000 reliable stress measurements into one giant database. The goal was to see if any patterns would pop out of what everyone just assumed was pure geological chaos. And what they found was absolutely stunning. The project leader, MD Zobach, put it perfectly. He said, their work showed that the Earth's stress field isn't chaotic at all. Far from it. Instead, they found these incredibly consistent, predictable patterns stretching across huge chunks of the planet. So the world's stress map showed us that these huge parts of our continents have these incredibly uniform stress fields. I mean, for example, pretty much all of North America east of the Rockies is being squeezed in the exact same direction, northeast to southwest. And these patterns aren't just a surface thing. They're consistent from a few kilometers deep all the way down to the base of the crust. They're a direct reflection of the massive tectonic forces acting on the plates. For the very first time, we had a map of the Earth's invisible squeeze. Which, of course, brings us to the big question. So what? Now that we can actually map these powerful, invisible forces, what do we do with that knowledge? How does it change how we look for energy, how we prepare for earthquakes, how we manage the stability of the very ground we build our entire world on? The map is drawn. The next chapter is all about figuring out how to use it.